Hi everybody, welcome back to the Feynman Technique. So today we are going to take a look at this trigonometric integral right here, and we're going to call this the trigonometric beta function because it relates back to the beta function. And from our previous work, we have several formulas that we can relate back to the gamma function or the beta function that involve the gamma function. So we are going to express this in terms of the gamma function. So let's go. All right, so the beta function is defined like this. This is just the standard integral definition of the beta function. So we'll be using that. And we'll also use the beta-gamma relationship. We derived this in our last video. That is beta of u comma v is equal to gamma of u, gamma v over gamma u plus v. All right, next we're going to make the substitution that t is equal to sine squared x. Therefore, dt is 2 sine x cosine x. And our bounds change from 0 to pi over 2 to 0 to 1. And we'll notice that 1 minus t is just 1 minus sine squared x, which is cosine squared x. So now our beta function can be written like this. Well, that kind of looks like what we started with. Not quite though. All right. So we have beta of uv is equal to this, but don't forget we have to replace our dt. And our dt is 2 sine x cosine x dx. All right. So now we'll rewrite our sine terms in blue here. You see this is just sine squared to the u minus 1, so that becomes sine to the 2u minus 2. Similarly, cosine becomes cosine to the 2v minus 2, and then we have our differential over here. And this will combine to give us this, and then this. All right, so this is, again, we just modified our beta function definition right here. So now we have beta of u and v is equal to this. Well, that means that this integral, which is, it's starting to look more and more like what we need, is equal to this. So now we have an integral in terms of sine u and cosine v expressed as the beta function, half the beta function of u and v. So next, we're just going to redefine some variables here. These are constant variables. We're just going to let 2u minus 1 equal a and 2v minus 1 equal b, implying that u is equal to a plus 1 over 2 and v is equal to b plus 1 over 2. Plugging those back in, and now we have, this is our original integral. That's what we originally set out to solve. And we see that it's equal to 1/2 of the beta function evaluated at these values. And now we're going to use the beta-gamma relationship and plug it in. And we just kind of have the ultimate cheat code here for any integral like this. And for integers a and b, this is going to turn out to be this is going to turn out nice. Because half integer multiples of the gamma function evaluate to something involving square root of pi. So you can see that for integer values of a and b, we're actually going to get an elementary result for this. So anyway, guys, I hope you enjoyed that, and we'll see you next time.